Hi everyone. Let's follow the signal from the input of this amplifier right to the output section. And I'm going to show you a few tricks in here so that you can run your amplifier without having to have a speaker on it, yet feed a really crazy signal into the input. And when I say crazy, I mean, pretty high amplitude signal into the input, and you won't damage anything. So there's a bunch of tricks that are, I guess used by people that work on amplifiers and design amplifiers. And this is one of them, and this really isn't talked about. Now, I've talked in the past a lot about running amplifiers without a speaker just for mild testing, and that is absolutely fine as well. And I'll touch on that when I show you what to do here in just a moment. So what I've done is I've got this old oscilloscope that we looked at in that video on YouTube. Now, this thing was free. The probe that's attached to it is absolutely ugly, and it's free too. And as you can see, somebody had done this in the past. I just pulled this out of my scrap bin. It's a direct probe. There's none of this 10-to-1 fanciness. It's right from the probe right to the input. And I'm going to show you how you can troubleshoot a lot of electronic gear with the most basic equipment possible. And this is about as basic as it gets, and it was free. Now, a lot of times things like this show up for free at ham radio swap meets and all sorts of places like that. Just online auctions. People are, giving these things away for, relatively cheap, and if not free at some times. So this was free to me. Probe was free, and we're going to use this free equipment to follow the signal through an amplifier, and I'll show you how to do this even if the oscilloscope is compromised itself. So we know that the horizontal sweep in this thing isn't very linear, and I'll show you how to just look beyond that. These are all the tricks to make you an extremely good technician and with the most basic pieces of equipment. So let's get started. All right, I've got a coffee brewing. It's a late night in the lab here. So what we're going to do is we're going to follow a signal from the input to the output. And I want to use all the gain stages. Some of them not so gainy, I guess you could say, but I'll explain that as I go along. But I'm going to follow all the stages all the way to the output. So I'm going to use one of these 3 jacks up here. If I use one of these, we're going to miss this phono input area here. So we'll just start right from the beginning, so from the very input grid right to the phase inverters here. So what we want to remember is pin 2 and pin 7. That's the grid or both grids of the 12AX7 and the 12AU7. All right, all of these tubes are relatively close. The 12AX7, 12AU7, 12AY7, 12AV7, 12AT7, the 6CG7. They're all very close to each other with their pinouts. The 6CG7, of course, has a 6-volt filament that's not center tapped, and the 12AX7 has a 12.6 volt, if you want to call it that, and a 6.3 volt center tap filament, so you can use it for dual service. Probably the 12AX7 and 12AU7 are probably the 2 most famous vacuum tubes on the planet. Because of guitar amplifiers, back when televisions were prevalent, the 6GH8A and 6GH8, I think, were probably the most prevalent tubes on the planet. So what we want to do here is we want to just follow the signal. So we're going to go from grid to grid. And of course, if we had a signal that's missing anywhere, then we would know okay, so if it's on this grid, but we don't have a signal on, pin 7 over here. So if it's on pin 2 grid, and it's not getting to pin 7, we know that the problem's in here somewhere, right? And it's the same thing with this. If we had a signal on pin 2, but we don't have anything on, on this pin 7 here, we'd know that the problem is either this plate resistor or the coupling cap, maybe an open cathode resistor, something like that. And at that point, you can even refine from the scope right down to something as simple as a DMM to locate that issue. Okay, so I'll explain this as I'm going along here. Now, I was talking earlier about a trick that allows you to run these amplifiers without having to have a speaker attached, and you can, vary the gain level wildly on the input. That's very simple. All you want to do is disconnect the coupling caps from the phase inverter to the 2 output tubes. So you want to make sure that the bias is still intact. Don't ever unhook the bias, okay? Very important. So you just want to unhook these coupling caps, and as you can see, these are kind of just free floating here right now. So the output tubes are just getting no signal. So they're biased, the screens are there, everything's there. They're just going, where's my signal, all right? Now, because of that, we have a feedback circuit that runs back up into this area here. So the signals beyond this point are going to get kind of ugly because of, this whole area it's a loop right in this area right here. So we've unhooked these so we can, comfortably get to about this area over here, maybe this here, and then after that, it's going to probably start to look a little bit square wavy because, this when you attach feedback, you get a gain drop, things like that, right? All of this whole network is unhooked. But this is a very useful technique if you want to troubleshoot anything in preamplifier stages or anything like that. You don't want to have a speaker blasting away in the background, or you don't want to have a dummy load on the amplifier that's going to be getting very hot because you've got, different, a variation of signal levels running on the input. It's also a lot easier on the output transformer and things like that. Now, in the past, here's another little trick for you. In the past, I've told you that you can run these amplifiers without a speaker, but you only have to make sure that you have a very low level audio signal coming in. You can't give it very much audio. If you ever turn the audio up and you hear the audio transformer singing on the chassis, making the tone, you know that level's getting pretty high and you don't want to do that. Now, tubes, just by the way that they're built, are high impedance devices. And, when you open the winding on the secondary portion here, the impedance does go very high. And a lot of the times, coming from a ham radio operator and somebody who's done a lot of experimenting with vacuum tubes and building power amplifiers and things like that, very rarely will you harm an output tube if there is no speaker, and even if you give it just a short blast of audio. Now, when you're in a transmitting situation, if this was a modulator transformer and it was in a transmitter, you might hurt something, right? You got to be very careful with that. But in an audio amplifier, a slight mistake of giving it just a burst of audio much of the time won't cause any kind of issues. Now, again, you don't want to run anything with a substantial signal level into it without a speaker or without a load, just for a long period of time, just because the plate impedance of these tubes dramatically changes if there's no load on the secondary side. Okay, so there is a balance point. Again, very small level signal. So if you were to feed a signal into the input of this amplifier, okay, so you're feeding a signal in over here, and you hooked a speaker up to it, and it was just a very, very mild, like a tone, very, very light tone, it's not going to hurt it. Okay, but if you touch the speaker on it and wants to blow the cone out of the speaker, you're probably going to harm the tubes and things like that. So just common sense, all right? So that's all you got to do. Your mileage may vary depending on the design. A lot of designs aren't very stable. More intricate designs like this are extremely stable. So it just depends on the vacuum tube designer. If you've got something from, Joe up the street who put an amplifier together and hasn't done the correct testing, and you run it without a load, it might break into oscillations and things like that, right? So again, your mileage varies. I can just look at this schematic and go, okay, this thing is going to be rock stable without any signal on these tubes. It's this is an extreme design for a vacuum tube amplifier. It really is. It's like, okay, what else can we add? Okay, what else can we do? It seems like they just puzzled over this, and they did a nice job. It's a little bit too extreme, put it that way. It could have been a lot simpler than this, and you'd get the same result, maybe even a better result. But this is the way they put it together back in the day. And, I'm not designing this amp. I'm just showing you how to service amplifiers like this and follow schematics. So what I'm going to do now is I am going to back the lens out. So it's going to have to be a little ways away from the schematic because I have to get both of these in here. The reason that I'm not going to do picture-in-picture is because it puts the scope in a very small corner of the video, and you don't get to see me adjusting the scope very well. So you can see me fiddling with all the controls, and I'll just point to things. So you'll have the schematic. The schematic is below the last video. So the previous video to this one will have the schematic. I won't re-upload the same schematic again to this video because it's exactly the same thing. So one video down, the schematic is there. It's high res, just like this. Looks very nice. And you can follow along with that schematic. Now, before I get working on this and I start probing in this, I have to warn all of you that are new to this or that are used to solid state stuff or that just don't know about this stuff. These amplifiers have extreme voltages in them, and the capacitors, they charge up and give quite a substantial amount of current once everything is charged. So if you're working on something like this, you're doing so at your own risk. Resting your hand on this by accident can be a very, very bad mistake. There's high voltage everywhere in these amps, and that's the way it is with all of these amplifiers. Any type of vacuum tube amplifier, radio receiver, piece of test equipment, oscilloscope, television, whatever you have, anything that has vacuum tubes in it, and even some of the more modern electronics with solid state stuff in it has pretty high voltages in it as well. Some of the very large amplifiers have got, collector voltages that are crazy. So if you're following along, you're doing so at your own risk. Just know that these things are loaded with high voltage and you have to take all the precautions. If you're unfamiliar with this, don't work on a vacuum tube amplifier until you feel comfortable with it. And if you don't feel comfortable with it, just don't work on them. All right. So again, like this is recessed, right, in the chassis. This thing is like more towards me. When you put the bottom of this amplifier on, it's so close to the bottom that they put a piece of cardboard on it. It's even squished on the cardboard. I don't know why they did this. I think they wanted this to convection cool a little bit easier. So they have this recessed into here, and actually, no, it won't even convection. Well, yeah, it will. It does have breathing holes here. Not very many, though. But, yeah, they've recessed this into the chassis, maybe for top clearance. I would think that would be the only thing. But the bottom pan touches this with the cardboard. It's like actually pressed onto this socket. Why they did that, I really don't know. They should have made the chassis maybe just a bit deeper or something like that. I don't like that in the design at all. But at any rate, this is more towards me. So if I was to be working on this and I did this, oh, that would be bad news. There's 600 volts on these two output tubes. So if I was to rest my hand on there, I would be having a very, very bad day. One other thing I'm going to show you is this oscilloscope here, again, was free, and so was a scope probe. And this is the way these old, ICO probes came. They had a really long exposed tip. So I've got a piece of this fibrous tubing that I talk about all the time. And in my next video, I'm going to put an entire list of all of this stuff that I really prefer to use. So I'm going to make a video that has my preferred tools, my preferred solder, my preferred little things like this, the tubing, all this kind of stuff, the wiring I use, all this. I'm going to make a huge list, and I'm going to display some of this in the next video. So for all of you that want to know all my favorite stuff, you'll see that here coming up very shortly. At any rate, this is a piece of that tubing, that fibrous tubing. So what I'm going to do is it's tight here, but it slips up over this, and it only exposes just the tip. So when I'm touching things, I'm not touching multiple things and shorting things out. All right, so you can see that, I'll move this out of the way here. I'll just zoom on in one more time for you. So you can see if I was, going to come into here like this and touch something, right? Say I was going to touch this, I could very easily slip and touch them both at the same time. This prevents that from happening, so I don't really have to worry about that. All right, so something to keep in mind, just a little piece of fibrous tubing here can really be your friend when you're working with a probe like this. Now again, this is the system that I've got going on here is very, very basic, and I'm doing this just to show you that you can troubleshoot with pretty much any old piece of test equipment. Now I'm going to restore this, and I will use this in many videos just to give you an example of how you can use this for many, many different pieces of troubleshooting. Old radios, switch mode power supplies, you can use this thing for so many different things, and it's just absolutely fine. So if you have a chance to get an older scope like this or a brand new one, whatever you can afford, anything with a visual means is going to help you. Put it that way. Once this is restored, the horizontal linearity will probably get just a little bit better on this scope. Probably won't be fantastic, but it'll be a little bit better. But I'm not worried about horizontal linearity on this thing whatsoever, because that doesn't affect our testing. All right, I have a cup of my favorite dark roast coffee, which means life is good. Let's get following a signal. All right, so I have my signal from the signal generator attached to the low mag input right here, and that's this little area right here. The amplifier right now is live, it's plugged in, there's full B plus all over this, so I have to be very careful when I put this down, that I do not put this down and touch my hand on anything. So, signal coming in here, we want to see if it's going to get through this area and up to the grid of the very first stage, and that's pin 2. So the very first thing that you want to do is get your scope set up so that you can see a comfortable signal on there, and that's very easy to do. So you would just connect your scope to the signal generator, have the gain at its maximum because you want that for this particular portion of the test. Turn your signal generator up, until you get a substantial looking signal on there, and look at that. Doesn't that look nice? That is a beautiful signal from an oscilloscope from 1930 something or other. You can see the horizontal isn't completely linear. Who cares? We're not looking at time. We're looking at amplitude. So time, amplitude. All right, and we can even tell distortion and everything, even though the trace isn't linear. No problems whatsoever. Again, that's very, very easy to overlook that issue. Again, when this is rebuilt, it'll be all that much better. Okay, so that's the signal at the input jack. So now what we want to do is we want to see if that signal is getting to the grid of the very first stage right here. Okay, so that'd be pin 2 of this tube. Again, the schematic is down below the previous video if you want to download it right here. You print it off or do whatever you want. So I'm going to be looking at this area right here, pin 2. Okay, and that's right at the end of this resistor here. So I'll just touch this and look at that. We have a signal right there. So we know already that the signal is getting from the input jack through the switching here and right up to that grid. So we know we're good for signal at the input of the phono amplifier stage. Now what we want to do is we want to see if it's getting through this stage and into the grid of the next stage. Okay, and that's pin number 7. Okay, so this down here is pin number 7. And look at that, how much amplification there is, right? So that's the next stage, all right? This is the first. So this is input, and then this is the input to the next stage. So you can see that we're getting quite a bit of amplification. So at this point, what you want to do is turn your signal generator down. That's your cue to do that. So what I'll do is I'll turn the generator down, like so. And as you can see, the distortion in there is really, really wild. There's lots of distortion. So you can turn that down until you get a decent looking signal, and that would be right about there. And now we know that we're not overdriving that stage now. Okay, so now we're not overdriving this. And that's very important. Now you can leave an overdriven signal in there if you want to do some hardcore signal tracing if it's really dropping out somewhere, but in this case we don't need to do that just yet, or at all. So now that we've gone here to number 7, I'll just get something else to point with here other than my probe. Let's see, what do I have? A Q-tip? Nah. Capacitor? No. Oh, here. It's my thing for my touch scope. Okay, so what we're going to do is we're going to look at the signal right here after this 0.22. That's not what it is. Yes, 0.22 microfarad capacitor. Now, I don't want to touch my probe onto the plate circuit here because I'm going to charge that cap inside here that I told you about. All right, and if you have a speaker hooked up to something like this, all right, and you charge that cap up and say you're troubleshooting just a very low level signal, and then you touch that probe and you discharge, say, 160 some odd volts of plate voltage into the grid of that stage, you're gonna get a pretty nasty pop out of that speaker. So I want to avoid that, so I don't need to see the DC here because the scope is all AC coupled anyways. So I just want to see the AC signal. So I'm going to use this very leaky capacitor, and whatever DC it's leaking, we'll have to deal with it. But we're going to take a look at this right here at this point, and we should get some pretty big amplification. So we'll look at pin 7 here, and then we'll compare it to the output here, which is going through this 0.22 capacitor, 22 microfarad. So that's off of pin 6, comes down, and then we have our 0.22 microfarad at, what is that, 200 volts it says there. Okay, so let's check this spot. And that spot there is this point right here, okay? So what I'll do is, I'll show you the grid again. So this is the input to that stage on the scope. I can get that in there. That's the input. Now what do you think is going to happen when we look at the output of that stage? Whoa, look at the amplification there. So now we need to turn the gain of the scope down. And there we have it. And that's a nice clean looking signal. And that's coming out of there. Now, of course, we could drive this right into distortion by turning the signal generator up. I'll show you that, right? Because we knew earlier that it's going to get distorted. You can see how it's squaring off at the top and it's turning into a peak at the bottom. And you can really see, we can really drive that into distortion. You know, that would make a lot of guitar players that are wanting this kind of stuff very happy right there. Lots of different types of distortion in these amplifiers. You have preamp distortion, you have output stage distortion. This would be known as preamp distortion. All right, so you can see we can vary that. So I'll drop that back down right to about there. It's a nice clean signal. And that is there. So we know that this whole stage is working now. If I was to go back to the very input where we were looking at this before, look at that. We can't see hardly anything because there's so much amplification in this one tube here. Now there's 2 triodes in there, so we have 2 stages in one tube. Input signal, output signal. Just that simple with the scope, and we know that that stage is working. That easy. Old scope. Who cares about time? Only amplitude, right? And even the amplitude, we don't even need to measure the amplitude. We can just tell now that we've adjusted the scope in the signal generator so that we have, we can barely see the signal on the input, right? You see it just jiggling there a little bit. And we have so much amplitude on the output, we know that the stage is amplifying just fine. And my signal generator is, putting very low signal into this thing, right? And look at even the scope is turned right down. The vertical gain is, sensitivity is turned right down there, right? So that stage is working beautifully. No problems there. All right. Let's follow the signal through this switching network here all the way over to the phase inverter. So let's check out pin number 2. Let's see, from this point right here, and then we're going to go all the way over here to pin number 7. Now, we don't need to understand the way the switches work as long as we have signal at this point. That's the difference between troubleshooting and designing an amplifier. If there was a problem in this stage, then we would have to start figuring out how this works. But if we get signal through this, we can ignore all that and just work our way along really quickly. So we'll take a look at the signal here, and then we'll take a look at the signal here. So first pin 2 and pin 7 of the second tube, and that's that tube right there. Okay, so let's move this out of the way. So let's go to pin 2 right here. And there's our signal, no problems, right? Now let's go from pin 2 to pin 7 over on this side over here, right through the switching. All right, so pin 7 is right here. And look at that. No problems. A little bit of amplification there as well. All right. Now what we can do is we can vary the gain of the signal generator here. Turn the gain of the signal gen down just a little bit so that we can keep things nice and clean right about there. And we can turn the gain of the scope. I think it's about max for the scope right about there. It doesn't really change much after that. So it's looking good. Right? No problems there whatsoever. Okay, so now we're at pin 7. So we've now successfully followed the trail. We know everything is okay up to this point. There's no problems right here, right? And if you want to take a look at gain differences, like you can see how much things are changing all the way through the stage here. So I'll go right back to our last stage right here, right? I'll go right back to here. I'll turn the signal generator up just a little bit so we can get a bit bigger of a signal on the screen. Okay, see that right there? Now what I'll do is I'll go right back to the input. Okay, so this is where the signal's coming in. Look at that. Just a jiggle of the line. Nothing there, right? Very, very low signal, all right? So we can go to the output of the first stage again. We can get that on there. A little bit more of a jiggle. Output of that stage, right? And then all the way through here, all the way to the output of our, or the input of our last stage that we tested. And you can see, right? You can see the difference in gain. That first stage, you know, for the phono was really adding a lot of gain in there, right? So no problems. So at this point, we would know that we have a path all the way from the input right up to this point right here, to the input of this stage right here. We've verified this entire area, just that easy, with this old clunky oscilloscope and a rather scary looking oscilloscope probe, okay? So now what we want to do is we want to go over here. Let's check out the gain here. Now we're going to get some attenuation because this is a volume, or a bass and a treble circuit with a volume right over here, okay? So we're going to get attenuation right here to this point, but if we go past the volume control over here, we should get some amplification again because we have another triode to amplify this again. So whenever you're adding stages like this, you usually end up with some form of attenuation at this point. So don't be fooled by that, and I'll show you that right now, okay? So remember what we saw here at pin 7. Let's again look here at pin number 2 of the next stage, okay? So we saw pin number 7 here, right? So now let's go to pin 2 of the next stage. Look at that, how small that is. Right now you might be thinking, whoa, you know, we're losing signal in there. That's standard when you're dealing with a bass and a treble control. Right? In order to bring that back up again, they're going to use the next triode here to amplify that, right? And it's going to be at the grid of the next tube here. So we're going to be roughly close to where we were before. So now we're going to go to that stage, which is number 7. And look at that, how much there is there. Right? They're really making up for that loss. So I can turn this back down. Now, since I'm at the volume control area, right, that's pin 7 here. You can see the wiper. It's kind of hard to do holding the probe in one hand, but I'll attempt to do this. See the wiper of the volume control right here? Right at pin 7, there's the grid right there. And that's the wiper. So if I move the volume control around, we should see this move. Okay, so I'll grab the volume control. Look at that. No problems with the volume control at all. Right down to nothing and right back up. So we know the volume control works. There's a step attenuator here. You can see how the trace gets kind of crunchy as I'm doing that? See that kind of crunchiness there? You know what that is? That's a dirty control. So that needs some contact cleaner. Okay. The volume control is pretty good. There's no scratchiness in it. It's nice and smooth. No problems with that. Just the attenuator's got a bit of grunginess going on there, and that's pretty common with these open type switches, right? Dust settles on them and everything like that. So that is noise. That's like that scratching noise that you can see the scratching on the scope there. That's that scratching noise that you would normally hear in a speaker. Okay. Right. And no speakers needed. All done visually. Okay. So now we're at this point right here. So now you can see we have a cathode attached into the feedback area here. And this is our phase inverter circuit. So we're going to get probably a distorted signal at the next grid because we have no hookup over here. So there's no loop happening, but we'll go there anyways. So pin number 7 of the next tube, which is the 6CG7, which should be over here. Not to be confused with that one. That one is the regulator, so you don't want to be probing that one. So let's go. Where's the index on this one? Let's take a look. That looks like the index right there. Like it looks like they've actually burnt a piece of the pipe that they've used too to solder the pin. I don't want to touch that with my other pointer because it's conductive. Let's see, what have I got to point with? The only thing I've got that's non-conductive right now on my bench is a glue stick. Look at that. So this right here, you see I'm moving this right down here. It's a little bit of a burn there. I don't know if you can see that. Zoom on in a little further. There's a little bit of a burn here right where it touches this pin. That pin right there and right here is a burn. So it's not as viewable on camera as it is in person, but that's a pretty bad burn. That looks like it almost might be through the insulation, which is not a good thing. All right, so again, we're looking at pin 7, right? That's right, we were because they reversed this on the 6CG7. So pin 7 and pin 2, right? So if we go to pin 7, we're probably going to see some form of distortion. Let's see if my claims are correct here. Oh yeah, look at that, eh? Right off the screen. Yes, and there is a lot of distortion there. Look at that, because the loop is broken, right? Even looks like we have some form of crossover distortion happening right here. See that? So lots of distortion there. So we're not going to be able to look at the signals in this stage unless we hook up a speaker, right? And that's obviously known because we've broken the feedback loop to troubleshoot up to this point. So we can troubleshoot right up to this point right here with no speaker attached. Now, if we wanted to troubleshoot the last 2 stages, we would just hook up a speaker or a dummy load. So an 8 ohm speaker or an 8 ohm, just a large resistor to the output, and then we would keep the amplitude down so that we're not heating up that resistor and exercising the audio output transformer, and we just find a sine wave on the output like we normally have that we've been finding all the way through. All right, I have my remote display unit hooked up here for my meter, so the meter's off to the side. It allows me to fit that comfortably into the shot. Let's see what the plate voltage is on the 6AV5s. So Bogan was known to be a little bit extreme. And let's see what we're talking about here. That's pretty extreme. Bogan, you wild man. 661 volts, 662 volts on the plates of this thing. We're in 6146 or 807 territory right now. We're dealing with transmitter type voltages. That is extremely high. So since that's extremely high, we're going to have a pretty low screen. So let's check out the screen. If the screen was very high, this thing would be glowing like a reactor. So let's see here. Pin 8 is the screen, and that would be here. It's very easy to see the plate because it's the line that runs into the audio output transformer. Screen's not so easy, so that's pin 8. 6AV5 is kind of a tube on its own. A lot of the time in power output tubes, pin 8 is the cathode. All right, so in this case, it's the screen. So you can't directly sub tubes in this thing without rewiring the sockets. 176, that is a pretty low screen voltage, and that's the reason that those 6AV5s are not doing very bad things. So that's why they're doing this. So very high plate voltage and, pretty low screen voltage. So not bad. So now this is the regulated output of that regulator tube. So we got this regulator right here. Now there is no reference to this thing. And that means that it's the way they've got this attached, it's going to be pretty much watching load variation, not line variation. So let's see what happens here. Let's, for the fun of it, I'll just, here, I'll put this up here. All right, so let's take a look at this and let's see what the line, I'll vary the line just a little bit and we'll see what happens. Yeah. Not so good with line variation. Okay. So now what I'll do is give me one moment and I will be right back and I will go grab a substantial resistor and we can load the screen and see what that does. All right, I have a resistor that I can load the the screen's with here, so I can load the screen supply. It's a 10K ohms, 20 watt resistor, and I'll just ground this to the chassis here very carefully, watching my hands. Don't try this at home. This is well insulated, so I'm going to hold the ceramic body. And what I'm going to do is I'm just going to touch this onto the screen grid pin, and we'll see what this does. All right, so we're dealing with 175 volts here, and it's 10K ohm, so about 17 milliamps, something like that. Okay, we'll just in the rough area. This be about what I'm adding here. So now let's take a look, see what happens. So 175, I'm going to add 10K, so it's going to drag it down. We're going to pull another 17.5 milliamps, which is substantial. That's a pretty large load for this supply. Okay, so here we go. Not bad. Wow, not bad for pretty much, I guess you could say, error ampless type of supply, or a regulated supply. Like, I mean, error amplifier kind of nil in this, and no reference. That's not bad, from 175.6 down to 173.5, 0.3, something like that, and that's adding 17 mils worth of load right there, or around that. And the resistor's getting warm. Nice and warm. So there you have it. That's very good. Now, moving 3 volts or something like that in a situation like this on the screens is nothing, okay? This isn't a transistorized piece of equipment where things have to be regulated, beyond the decimal kind of thing. This is absolutely fine. So that is actually very impressive, Mr. Bogan. That's very impressive for, a regulator, pass tube, and, somewhat, I guess you could call it a crude air amplifier kind of idea in this. It's not bad. So as I say, this is more, I guess you could say, dealing with load variation, not so much line. So you'd want to have a relatively stable line with this, and that way everything would stay okay. Not bad. So anyways, there you have it. So about 170 on the screens, and that's with my line voltage here. This is, of course, on an isolation transformer and current limited variac supply, right? So this isn't plugged directly into the line. This is isolated right now. So not too bad. So 175, and of course, craziness on the plates. Look at that, 660 volts. Again, this is transmitter territory, right? Some of the large transmitters have this on their modulator tubes. You have Johnsons and things like that. In some cases a little higher, but we're still getting up there. That's pretty crazy there, David Bogan. Most of these amplifiers that put out big power, 450 on the plates, something like that. And David Bogan, whatever. Well, let's put 660 on it. It says here 605. I think it is 605. So again, we're dealing with a bit of line variation here. This is at 117, right? I'm probably giving this about 120, something like that. So not bad. That's fine. By the way, that's absolutely fine. If you get voltages like this in an amplifier that are over what they say they are, so everything's going to be a little bit elevated, right? So here it says 105 for the plates of the input amplifier here, and that would be these right here, and it's 124. That's nothing to worry about. Who cares? That's not a big deal. All right, don't let that bother you. It's just it's a little bit higher plate voltages. Again, these aren't transistors, right? That little bit of voltage variation on a vacuum tube like this in an amplifier stage means 0. Okay? Not a big deal. Not a big deal whatsoever. If this was, say, in some form of a metering circuit where everything had to be regulated and there was, references, like, 0A2s or 0B2s or whatever in there, and they were acting as references with their amplifiers and 6AS7s and things like that. If it had to be, say, 105 volts right on, it would have to be 105 volts. But this is an amplifier, and this is all unregulated from the transformer. The only thing that's really regulated is the screens on these. Something to keep in mind. Whenever you're working on these amplifiers, don't get too hung up on that. I see a lot of people get caught on that. They're going, oh, it's so much higher. What are we going to do? There's something really wrong. Absolutely nothing wrong. In fact, with these elevated voltages, I'm not going to lie, this amplifier is going to sound even better. Okay? So now, let's for pure randomness, let's check this capacitor right here. It's at a pretty easy place to get at. I can get at both sides of this. This is a waxine here. This is this 0.1 at 400. Okay, so what I'll do is I'll touch this side here. What have we got on the plates of that? Oh, come on, just read it. Not getting a very good connection here. 159, okay. So 159 there. Let's see what's on the other side. 0.8 of a volt. That is a mighty leaky capacitor. And that's not even with an active probe or anything like that, a powered probe. So this is probably closer to a volt. Now you have to keep in mind that the meter itself is going to load this circuit. So what I'll do, just for fun's sake, is I'm going to hook up my powered probe, and let's take a look at the difference. So that'll virtually almost nullify what we see here. So it's 0.8 of a volt. So we're going to probably be closer to 1 volt. And that 1 volt is changing the way that the circuit works. It's not supposed to be passing DC. Okay, so give me 1 sec. I'll be right back. All right, let's see how much the meter is actually loading the circuit. So I have my probe here. That is into the gigohms, way, way, way up there. So I don't really have to worry about any circuit loading here. Let's see what this is at. So about 0.9. So we're dealing with about 0.1 of a volt difference. And that is what the meter is giving us. So we were at 0.9 there. So let's just quickly go back. The line voltage variation might be changing here again, so I'm not so sure about that. I'm just going to ground the probe out. I always do that when I'm done. You see that? Ground the probe out to protect it, and as you can see, it zeroes out. You got to be very careful with that probe because it is extremely sensitive to static. I'm just going to remove the probes now, so you're going to see some movement here. And I'll put this back in again. There we go. And I'll grab the positive probe here, and this is, again, not active, so there's no active probes right into the meter. So you can see that, yeah, about 0.1 of a volt difference. Now, in some cases, that's extremely substantial. And in this case, of course, we're changing the bias point. We're changing bias points in here by doing this kind of thing. That's what these wax capacitors do. That should be at 0, right? There should be nothing there. It should be like chassis. So you can see that this is definitely leaking. We're almost getting a volt through this, right? So that's going to affect the next stage. Now, I know a lot of people like to leave these behind because they say, oh, it's the vintage thing, and, I don't want to change them if I don't have to. Well, that is not the way. This will be changing the way this amplifier sounded from the factory. It won't be sounding like this whatsoever. For all those guys out there that think this is going to, make the amp sound better, well, whenever these things start to pass DC, it drives the next stage harder into Class A, right? And sometimes that does make them sound a little nicer. This is true, but it's still, not running the way it's supposed to, not the way that Bogan designed it, because these things are just breaking down. These good all capacitors are definitely not good all. They're pretty much bad all now. So I can go around and test all of these, but there's an example of looking at some leakage in circuit. This one is exceptionally bad. 1 volt is pretty bad. If that's passing 1 volt and it's holding it pretty continuous, that's an exceptionally bad, exceptionally leaky capacitor. If I was to put that on my cap meter, it would be pretty ugly. So at any rate, so there you have it. We chased a signal through this thing. You got to see some pretty extreme plate voltages, and this is common in some of these amplifiers. As I say, David Bogan was a bit of a rebel there. And, we looked at some of the screens here. They're, 170 some odd volts. That's pretty tame on a screen. But you have to do that. If you have that kind of an elevated plate voltage, you got to bring the screens way down or you're going to have problems with your tubes turning into firecrackers. And that's about it. So there we go. If you'd like me to dive into anything else in this thing or whatever, just let me know in the comments below. And we'll do extra troubleshooting with this older type equipment. It's just that easy. So, you can use any type of DMM you want. They're pretty much all the same, right? This thing here is, the reason I have this one is because it has a remote head unit so that I can just move this around and get this in a shot. But, you can use pretty much any DMM for this type of work. Just make sure that it's, voltage, requirements are where they're supposed to be and all that kind of stuff. And you can troubleshoot this with that. Or if you have a VTVM, things like that, you can use that as well. VTVMs are kind of fun to use. So I have my fair share of those, and they do have their purpose. VTVMs are very nice when you're wanting to peak circuits up. Looking at the movement of a needle when you're trying to peak something up is much nicer than looking at digits dance around on a display. So I often get that question, why would you want to use a VTVM over something with an input like this? And there's your answer. VTVMs also have very high impedance inputs as well, so something to keep in mind. Hope you've enjoyed, and I will talk to you all very soon with that upcoming parts list. Okay, take care. Bye for now.